In the most basic of terms, subnetting is the process of taking a large network and splitting it up into many individual smaller subnetworks, or subnets. By the end of this lesson, you'll be able to explain why subnetting is necessary and describe how subnet masks extend what's possible with just network and host IDs. You'll also be able to discuss how a technique known as CIDR allows for even more flexibility than plain subnetting. Lastly, you'll be able to apply some basic binary math techniques to better understand how all of this works. Incorrect subnetting setups are a common problem you might run into as an IT support specialist, so it's important to have a strong understanding of how this works. That's a lot, so let's dive in. As you might remember from the last lesson, address classes give us a way to break the total global IP space into discrete networks. If you want to communicate with the IP address 9.100.100.100, core routers on the internet know that this IP belongs to the 9.0.0.0 Class A network. They then route the message to the gateway router responsible for the network by looking at the network ID. A gateway router specifically serves as the entry and exit path to a certain network. You can contrast this with core internet routers, which might only speak to other core routers. Once your packet gets to the gateway router for the 9.0.0.0 Class A network, that router is now responsible for getting that data to the proper system by looking at the host ID. This all makes sense until you remember that a single Class A network contains 16,777,216 individual IPs. That's just way too many devices to connect to the same router. This is where subnetting comes in. With subnets, you can split your large network up into many smaller ones. These individual subnets will all have their own gateway routers, serving as the ingress and egress point for each subnet. So far, we've learned about network IDs, which are used to identify networks, and host IDs, which are used to identify individual hosts. If we want to split things up even further, and we do, we'll need to introduce a third concept, the subnet ID. You might remember that an IP address is just a 32-bit number. In a world without subnets, a certain number of these bits are used for the network ID, and a certain number of the bits are used for the host ID. In a world with subnetting, some bits that would normally comprise the host ID are actually used for the subnet ID. With all three of these IDs representable by a single IP address, we now have a single 32-bit number that can be accurately delivered across many different networks. At the internet level, core routers only care about the network ID and use this to send the datagram along to the appropriate gateway router to that network. That gateway router then has some additional information that it can use to send the datagram along to the destination machine or the next router in the path to get there. Finally, the host ID is used by that last router to deliver the datagram to the intended recipient machine. Subnet IDs are calculated via what's known as a subnet mask. Just like an IP address, subnet masks are 32-bit numbers that are normally written out as 4 octets in decimal. The easiest way to understand how subnet masks work is to compare one to an IP address. Warning, dense material ahead. We're about to get into some tough material, but it's super important to properly understand how subnet masks work because they're so frequently misunderstood. Subnet masks are often glossed over as magic numbers. People just memorize some of the common ones without fully understanding what's going on behind the scenes. In this course, we're really trying to ensure that you leave with a well-rounded networking education. So even though subnet masks can seem tricky at first, stick with it and you'll get the hang of it in no time. Just know that in the next video, we'll be covering some additional basics of binary math. Feel free to watch this video a second or third time after reviewing the material. Go at your own pace and you'll get there in the perfect amount of time. Let's work with the IP address 9.100.100.100 again. You might remember that each part of an IP address is an octet, which means that it consists of 8 bits. The number 9 in binary is just 1001. But since each octet needs 8 bits, we need to pad it with some zeros in front. As far as an IP address is concerned, having a number 9 as the first octet is actually represented as 00001001. Similarly, the numeral 100 as an 8-bit number is 01100100. So the entire binary representation of the IP address 9.100.100.100 is a lot of ones and zeros. A subnet mask is a binary number that has two sections. The beginning part, which is the mask itself, is a string of ones. Just zeros come after this. The subnet mask, which is the part of the number with all the ones, tells us what we can ignore when computing a host ID. The part with all the zeros tells us what to keep. Let's use the common subnet mask of 255.255.255.0. This would translate to 24 ones followed by 8 zeros. The purpose of the mask, or the part that's all ones, is to tell a router what part of an IP address is the subnet ID. You might remember that we already know how to get the network ID for an IP address. For 9.100.100.100, a Class A network, we know that this is just the first octet. This leaves us with the last 3 octets. Let's take those remaining octets and imagine them next to the subnet mask in binary form. The numbers in the remaining octets that have a corresponding 1 in the subnet mask are the subnet ID. The numbers in the remaining octets that have a corresponding 0 are the host ID. The size of a subnet is entirely defined by its subnet mask. So for example, with a subnet mask of 255.255.255.0, we know that only the last octet is available for host IDs, regardless of what size the network and subnet IDs are. A single 8-bit number can represent 256 different numbers, or more specifically, the numbers 0 through 255. This is a good time to point out that, in general, a subnet can usually only contain 2 less than the total number of host IDs available. Again, using a subnet mask of 255.255.255.0, we know that the octet available for host IDs can contain the numbers 0 through 255, but 0 is generally not used, and 255 is normally reserved as a broadcast address for the subnet. This means that really only the numbers 1 through 254 are available for assignment to a host. While this total number less than 2 approach is almost always true, generally speaking, you'll refer to the number of hosts available in a subnet as the entire number. So even if it's understood that 2 addresses aren't available for assignment, you'd still say that 8 bits of host ID space have 256 addresses available, not 254. This is because those other IPs are still IP addresses, even if they aren't assigned directly to a node on that subnet. Now, let's look at a subnet mask that doesn't draw its boundaries at an entire octet, or 8 bits of address. The subnet mask 255.255.255.224 would translate to 27 ones followed by 5 zeros. This means that we have 5 bits of host ID space, or a total of 32 addresses. This brings up a shorthand way of writing subnet masks. Let's say we're dealing with our old friend 9.100.100.100 with a subnet mask of 255.255.255.224. Since that subnet mask represents 27 ones followed by 5 zeros, a quicker way of referencing this is with the notation /27. The entire IP and subnet mask could be written out as 9.100.100.100/27. Neither notation is necessarily more common than the other, so it's important to understand both. That was a lot. Make sure to go back and watch this video again if you need a refresher. Or if you're a total whiz, you can move on to the next video on basic binary math. I'll see you there, or maybe here. Binary numbers can seem intimidating at first, since they look so different from decimal numbers. But as far as the basics go, the math behind counting, adding, or subtracting binary numbers is exactly the same as with decimal numbers. It's important to call out that there aren't different kinds of numbers. Numbers are universal. There are only different notations for how to reference them. Humans, most likely because most of us have 10 fingers and 10 toes, decided on using a system with 10 individual numerals used to represent all numbers. The numerals 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9 can be combined in ways to represent any whole number in existence. Because there are 10 total numerals in use in a decimal system, another way of referring to this is as base 10. Because of the constraints of how logic gates work inside of a processor, it's way easier for computers to think of things only in terms of 0 and 1. This is also known as binary or base 2. You can represent all whole numbers in binary in the same way you can in decimal. It just looks a little different. When you count in decimal, you move through all the numerals upward until you run out. Then you add a second column with a higher significance. Let's start counting at 0 until we get to 9. Once we get to 9, we basically just start over. We add a 1 to a new column, then start over at 0 in the original column. We repeat this process over and over in order to count all whole numbers. Counting in binary is exactly the same. It's just that you only have 2 numerals available. You start with 0, which is the same as 0 in decimal, then you increment once. Now you have 1, which is the same as 1 in decimal. Since we've already run out of numerals to use, it's time to add a new column. So now we have the number 1, 0, which is the same as 2 in decimal. 1, 1 is 3, 1, 0, 0 is 4, 1, 0, 1 is 5, 1, 1, 0 is 6, 1, 1, 1 is 7, etc. It's the exact same thing we do with decimal, just with fewer numerals at our disposal. When working with various computing technologies, you'll often run into the concept of bits, or ones and zeros. There's a pretty simple trick to figure out how many decimal numbers can be represented by a certain number of bits. If you have an 8-bit number, you can just perform the math 2 to the power of 8. This gives you 256, which lets you know that an 8-bit number can represent 256 decimal numbers. Or put another way, the numbers 0 through 255. A 4-bit number would be 2 to the power of 4, or 16 total numbers. A 16-bit number would be 2 to the power of 16, or 65,536 numbers. In order to tie this back to what you might already know, this trick doesn't only work for binary. It works for any number system. It's just the base changes. You might remember that we can also refer to binary as base 2 and decimal as base 10. All you need to do is swap out the base for what's being raised to the number of columns. For example, let's take a base 10 number with 2 columns of digits. This would translate to 10 to the power of 2. 10 to the power of 2 equals 100, which is exactly how many numbers you can represent with 2 columns of decimal digits, or the numbers 0 through 99. Similarly, 10 to the power of 3 is 1000, which is exactly how many numbers you can represent with 3 columns of decimal digits, or the numbers 0 through 999. Not only is counting in different bases the same, so is simple arithmetic like addition. In fact, binary addition is even simpler than any other base, since you only have 4 possible scenarios. 0 plus 0 equals 0, just like in decimal. 0 plus 1 equals 1, and 1 plus 0 equals 1. Should also look familiar. 1 plus 1 equals 1, 0. Looks a little different, but should still make sense. You carry a digit to the next column once you reach 10 in doing decimal addition. You carry a digit to the next column once you reach 2 when doing binary addition. Addition is what's known as an operator, and there are many operators that computers use to make calculations. 2 of the most important operators are OR and AND. In computer logic, a 1 represents true, and a 0 represents false. The way the OR operator works is you look at each digit, and if either of them is true, the result is true. The basic equation is x or y equals z, which could be read as if either x or y is true, then z is true. Otherwise, it's false. Therefore, 1 or 0 equals 1, but 0 or 0 equals 0. The operator AND does what it sounds like it does. It returns true if both values are true. Therefore, 1 and 1 equals 1, but 1 and 0 equals 0, and 0 and 0 equals 0, and so on. Now, you might be wondering why we've covered all of this. No, it's not to confuse you. It's all really to help explain subnet masks a bit more. A subnet mask is a way for a computer to use AND operators to determine if an IP address exists on the same network. This means that the host ID portion is also known, since it'll be anything left out. Let's use the binary representation of our favorite IP address, 9.100.100.100, and our favorite subnet mask, 255.255.255.0. Once you put one on top of the other and perform a binary AND operator on each column, you'll notice that the result is the network ID and subnet ID portion of our IP address, or 9.100.100. The computer that just performed this operation can now compare the result with its own network ID to determine if the address is on the same network or a different one. I bet you never thought you'd have a favorite IP address or subnet, but that's what happens in the wonderful world of basic binary math. Address classes were the first attempt at splitting up the global internet IP space. Subnetting was introduced when it became clear that address classes themselves weren't a sufficient way of keeping everything organized. But as the internet continued to grow, traditional subnetting just couldn't keep up. With traditional subnetting and the address classes, the network ID is always either 8-bit for Class A networks, 16-bit for Class B networks, or 24 bits for Class C networks. This means that there might only be 254 Class A networks in existence, but it also means there are 2,097,152 potential Class C networks. That's a lot of entries in a routing table. To top it all off, the sizing of these networks aren't always appropriate for the needs of most businesses. 254 hosts in a Class C network is too small for many use cases, but the 65,534 hosts available for use in a Class B network is often way too large. Many companies ended up with various adjoining Class C networks to meet their needs. That meant that routing tables ended up with a bunch of entries for a bunch of Class C networks that were all actually being routed to the same place. This is where CIDR, or classless interdomain routing, comes into play. CIDR is an even more flexible approach to describing blocks of IP addresses. It expands on the concept of subnetting by using subnet masks to demarcate networks. To demarcate something means to set something off. When discussing computer networking, you'll often hear the term demarcation point to describe where one network or system ends and another one begins. In our previous model, we relied on a network ID, subnet ID, and host ID to deliver an IP datagram to the correct location. With CIDR, the network ID and subnet ID are combined into one. CIDR is where we get the shorthand slash notation that we discussed in the earlier video on subnetting. This slash notation is also known as CIDR notation. CIDR basically just abandons the concept of address classes entirely, allowing an address to be defined by only two individual IDs. Let's take 9.100.100.100 with a net mask of 255.255.255.0. Remember, this can also be written as 9.100.100.100/24. In a world where we no longer care about the address class of this IP, all we need is what the network mask tells us to determine the network ID. In this case, that would be 9.100.100. The host ID remains the same. This practice not only simplifies how routers and other network devices need to think about parts of an IP address, but it also allows for more arbitrary network sizes. Before, network sizes were static. Think only Class A, Class B, or Class C, and only subnets could be of different sizes. CIDR allows for networks themselves to be differing sizes. Before this, if a company needed more addresses than a single Class C could provide, they'd need an entire second Class C. With CIDR, they could combine that address space into one contiguous chunk with a net mask of /23, or 255.255.254.0. This means that routers now only need to know one entry in their routing table to deliver traffic to these addresses instead of two. It's also important to call out that you get additional available host IDs out of this practice. Remember that you always lose 2 host IDs per network. So if a /24 network has 2 to the 8 or 256 potential hosts, you really only have 256 minus 2, or 254 available IPs to assign. If you need 2 networks of this size, you have a total of 254 plus 254, or 508 hosts. A single /23 network, on the other hand, is 2 to the 9, or 512. 512 minus 2, 510 hosts. Take a second and lock that into your memory. Then when you're ready, we have a short ungraded quiz for you before we move on to routing in the next lesson. The internet is an incredibly impressive technological achievement. It meshes together millions of individual networks and allows communications to flow between them. From almost anywhere in the world, you can now access data from almost anywhere else, often in just fractions of a second. The way communications happen across all these networks, allowing you to access data from the other side of the planet, is through routing. By the end of this lesson, you'll be able to describe the basics of routing and how routing tables work. You'll be able to define some of the major routing protocols and what they do, and identify non-routable address space and how it's used. You'll also gain an understanding of the RFC system and how it made the internet what it is today. All of these are very important skills in order to troubleshoot the networking issues you might run into as an IT support specialist. Routing is one of those things that is both very simple and very complex. At a very high level, what routing is and how routers work is actually pretty simple. But underneath the hood, routing is a very complex and technologically advanced topic. Entire books have been written about the topic. Today, most intensive routing issues are almost exclusively handled by ISPs and only the largest of companies. We'll arm you with the basic overview of routing to give you a well-rounded networking education, since it's an important topic to understand no matter what. But by no means will our coverage be exhaustive. From a very basic standpoint, a router is a network device that forwards traffic depending on the destination address of that traffic. A router is a device that has at least 2 network interfaces, since it has to be connected to 2 networks to do its job. Basic routing has just a few steps. 1. A router receives a packet of data on one of its interfaces. 2. The router examines the destination IP of this packet. 3. The router then looks up the destination network of this IP in its routing table. 4. The router forwards that out through the interface that's closest to the remote network, as determined by additional info within the routing table. These steps are repeated as often as needed until the traffic reaches its destination. Let's imagine a router connected to 2 networks. We'll call the first network Network A, and give it an address space of 192.168.1.0/24. We'll call the second network Network B, and give it an address space of 10.0.0.0/24. The router has an interface on each network. On network A, it has an IP of 192.168.1.1, and on network B, it has an IP of 10.0.0.254. Remember, IP addresses belong to networks, not individual nodes on a network. A computer on network A with an IP address of 192.168.1.100 sends a packet to the address 10.0.0.10. This computer knows that 10.0.0.10 isn't on its local subnet, so it sends this packet to the MAC address of its gateway, the router. The router's interface on network A receives the packet because it sees that destination MAC address belongs to it. The router then strips away the data link layer encapsulation, leaving the network layer contents, the IP datagram. Now, the router can directly inspect the IP datagram header for the destination IP field. it finds the destination IP of 10.0.0.10. The router looks at its routing table and sees that network B, or the 10.0.0.0/24 network, is the correct network for the destination IP. It also sees that this network is only one hop away. In fact, since it's directly connected, the router even has the MAC address for this IP in its ARP table. Next, the router needs to form a new packet to forward along to network B. It takes all of the data from the first IP datagram and duplicates it. But it decrements the TTL field by 1 and calculates a new checksum. Then it encapsulates this new IP datagram inside of a new Ethernet frame. This time, it sets its own MAC address of the interface on network B as the source MAC address. Since it has the MAC address of 10.0.0.10 in its ARP table, it sets that as the destination MAC address. Lastly, the packet is sent out of its interface on network B, and the data finally gets delivered to the node living at 10.0.0.10. That's a pretty basic example of how routing works, but let's make it a little more complicated and introduce a third network. Everything else is still the same. We have network A, whose address space is 192.168.1.0/24. We have network B, whose address space is 10.0.0.0/24. The router that bridges these two networks still has the IPs of 192.168.1.1 on network A and 10.0.0.254 on network B. But let's introduce a third network, network C. It has an address space of 172.16.1.0/23. There's a second router connecting network B and network C. Its interface on network B has an IP of 10.0.0.1, and its interface on network C has an IP of 172.16.1.1. This time around, our computer at 192.168.1.100 wants to send some data to the computer that has an IP of 172.16.1.100. We'll skip the data link layer stuff, but remember that it's still happening, of course. The computer at 192.168.1.100 knows that 172.16.1.100 is not on its local network, so it sends the packet to its gateway, the router between network A and network B. Again, the router inspects the content of this packet. It sees a destination address of 172.16.1.100, and through a lookup of its routing table, it knows that the quickest way to get to the 172.16.1.0/23 network is via another router with an IP of 10.0.0.1. The router decrements the TTL field and sends it along to the router of 10.0.0.1. This router then goes through the motions, knows that the destination IP of 172.16.1.100 is directly connected, and forwards the packet to its final destination. That's the basics of routing. The only difference between our examples and how things work on the internet is scale. Routers are usually connected to many more than just two networks. Very often, your traffic may have to cross a dozen routers before it reaches its final destination. And finally, in order to protect against breakages, core internet routers are typically connected in a mesh, meaning that there might be many different paths for a packet to take. Still, the concepts are all the same. Routers inspect the destination IP, look at their routing table to determine which path is the quickest, and forward the packet along the path. This happens over and over, every single packet making up every single bit of traffic all over the internet at all times. Pretty cool stuff, huh? During our earlier video on the basics of routing, you might have noticed a bunch of references to something known as a routing table. Routing itself is a pretty simple concept, and you'll find that routing tables aren't that much more complicated. The earliest routers were just regular computers of the era. They had two network interfaces, bridged two networks, and had a routing table that was manually updated. In fact, all major operating systems today still have a routing table that they consult before transmitting data. You could still build your own router today if you had a computer with two network interfaces and a manually updated routing table. Routing tables can vary a ton depending on the make and class of the router, but they all share a few things in common. The most basic routing table will have 4 columns. Destination network. This column would contain a row for each network that the router knows about. This is just the definition of the remote network, a network ID and a net mask. These could be stored in one column in CIDR notation, or the network ID and net mask might be in a separate column. Either way, it's the same concept. The router has a definition for a network and therefore knows what IP addresses might live on that network. When the router receives an incoming packet, it examines the destination IP address and determines which network it belongs to. A routing table will generally have a catch-all entry that matches any IP address that it doesn't have an explicit network listing for. Next hop. This is the IP address of the next router that should receive data intended for the destination network in question. Or this could just state the network is directly connected and that there aren't any additional hops needed. Total hops. This is the crucial part to understand routing and how routing tables work. On any complex network, like the internet, there will be lots of different paths to get from point A to point B. Routers try to pick the shortest possible path at all times to ensure timely delivery of data, but the shortest possible path to a destination network is something that could change over time, sometimes rapidly. Intermediary routers could go down, links could become disconnected, new routers could be introduced, traffic congestion could cause certain routes to become too slow to use. We'll get to know how routers know the shortest path in an upcoming video. For now, it's just important to know that for each next hop and each destination network, the router will have to keep track of how far away that destination currently is. That way, when it receives updated information from neighboring routers, it'll know if it currently knows about the best path or if a new, better path is available. Interface. The router also has to know which of its interfaces it should forward traffic matching the destination network out of. In most cases, routing tables are pretty simple. The really impressive part is that many core internet routers have millions of rows in their routing tables. These must be consulted for every single packet that flows through a router on its way to its final destination. What's also impressive is how much you've learned about routers, routing, and routing tables. Nice work. I'll see you in the next video on interior gateway protocols. We've covered the basics of how routing works and how routing tables are constructed, and they're both really pretty basic concepts. The real magic of routing is in the way that routing tables are always updated with new information about the quickest paths to destination networks. The protocols we'll be learning about in this video will help you identify routing problems on any network you might support. In order to learn about the world around them, routers use what are known as routing protocols. These are special protocols the routers use to speak to each other in order to share what information they might have. This is how a router on one side of the planet can eventually learn about the best path to a network on the other side of the planet. Routing protocols fall into 2 main categories: interior gateway protocols and exterior gateway protocols. Interior gateway protocols are further split into 2 categories: link state routing protocols and distance vector protocols. In this video, we'll cover the basics of interior gateway protocols. Interior gateway protocols are used by routers to share information within a single autonomous system. In networking terms, an autonomous system is a collection of networks that all fall under the control of a single network operator. The best example of this would be a large corporation that needs to route data between their many offices, and each of which might have their own local area network. Another example is the many routers employed by an internet service provider whose reaches are usually national in scale. You can contrast this with exterior gateway protocols, which are used for the exchange of information between independent autonomous systems. Spoiler alert, we'll cover exterior gateway protocols in an upcoming video. The two main types of interior gateway protocols are link state routing protocols and distance vector protocols. Their goals are super similar, but the routers that employ them share different kinds of data to get the job done. Distance vector protocols are an older standard. A router using a distance vector protocol basically just takes its routing table, which is a list of every network known to it and how far away these networks are in terms of hops. Then the router sends this list to every neighboring router, which is basically every router directly connected to it. In computer science, a list is known as a vector. This is why a protocol that just sends a list of distances to networks is known as a distance vector protocol. With a distance vector protocol, routers don't really know that much about the total state of an autonomous system. They just have some information about their immediate neighbors. For a basic glimpse into how distance vector protocols work, let's look at how two routers might influence each other's routing tables. Router A has a routing table with a bunch of entries. One of these entries is for 10.1.1.0/24 network, which we'll refer to as network X. Router A believes that the quickest path to network X is through its own interface 2, which is where router C is connected. Router A knows that sending data intended for network X through interface 2 to router C means it'll take 4 hops to get to the destination. Meanwhile, router B is only 2 hops removed from network X, and this is reflected in its routing table. Router B, using a distance vector protocol, sends the basic contents of its routing table to router A. Router A sees that network X is only 2 hops away from router B. Even with the extra hop to get from router A to router B, this means that network X is only 3 hops away from router A, if it forwards data to router B instead of router C. Armed with this new information, router A updates its routing table to reflect this. In order to reach network X in the fastest way, it should forward traffic through its own interface 1 to router B. Now, distance vector protocols are pretty simple, but they don't allow for a router to have much information about the state of the world outside of their own direct neighbors. Because of this, a router might be slow to react to a change in the network far away from it. This is why link state protocols were eventually invented. Routers using a link state protocol take a more sophisticated approach to determining the best path to a network. Link state protocols get their name because each router advertises the state of the link of each of its interfaces. These interfaces could be connected to other routers, or they could be direct connections to networks. The information about each router is propagated to every other router on the autonomous system. This means that every router on the system knows every detail about every other router in the system. Each router then uses this much larger set of information and runs complicated algorithms against it to determine what the best path to any destination network might be. Link state protocols require both more memory in order to hold all of this data and also much more processing power. This is because it has to run algorithms against this data in order to determine the quickest path to update the routing tables. As computer hardware has become more powerful and cheaper over the years, link state protocols have mostly made distance vector protocols outdated. Up next, we'll talk about exterior gateway protocols. See you there. Exterior gateway protocols are used to communicate data between routers representing the edges of an autonomous system. Since routers sharing data using interior gateway protocols are all under control of the same organization, routers use exterior gateway protocols when they need to share information across different organizations. Exterior gateway protocols are really key to the internet operating how it does today. So thanks, exterior gateway protocols. The internet is an enormous mesh of autonomous systems. At the highest levels, core internet routers need to know about autonomous systems in order to properly forward traffic. Since autonomous systems are known and defined collections of networks, getting data to the edge router of an autonomous system is the #1 goal of core internet routers. The IANA, or the Internet Assigned Numbers Authority, is a nonprofit organization that helps manage things like IP address allocation. The internet couldn't function without a single authority for these sorts of issues. Otherwise, anyone could try and use any IP space they wanted, which would cause total chaos online. Along with managing IP address allocation, the IANA is also responsible for ASN, or Autonomous System Number Allocation. ASNs are numbers assigned to individual autonomous systems. Just like IP addresses, ASNs are 32-bit numbers, but unlike IP addresses, they're normally referred to as just a single decimal number instead of being split out into readable bits. There are two reasons for this. First, IP addresses need to be able to represent a network ID portion and a host ID portion for each number. This is more easily accomplished by splitting the number in 4 sections of 8 bits, especially back in the day when address classes ruled the world. An ASN never needs to change in order for it to represent more networks or hosts. It's just the core internet routing tables that need to be updated to know what the ASN represents. Second, ASNs are looked at by humans far less often than IP addresses are. So, because it can be useful to be able to look at the IP 9.100.100.100 and know that 9.0.0.0/8 address space is owned by IBM, ASNs represent entire autonomous systems. Just being able to look up the fact that AS19604 belongs to IBM is enough. Unless you one day end up working at an internet service provider, understanding more details about how exterior gateway protocols work is out of scope for most people in IT. But grasping the basics of autonomous systems, ASNs, and how core internet routers route traffic between them is important to understand some of the basic building blocks of the internet. And now, a brief history lesson. Even as far back as 1996, it was obvious that the internet was growing at a rate that couldn't be sustained. When IP was first defined, it defined an IP address as a single 32-bit number. A single 32-bit number can represent 4,294,967,295 unique numbers, which definitely sounds like a lot, but as of 2017, there are an estimated 7.5 billion humans on Earth. This means that the IPv4 standard doesn't even have enough IP addresses available for every person on the planet. It also can't account for entire data centers filled with thousands and thousands of computers required for large-scale technology companies to operate. So, in 1996, RFC 1918 was published. RFC stands for Request for Comments, and is a long-standing way for those responsible for keeping the internet running to agree upon the standard requirements to do so. RFC 1918 outlined a number of networks that would be defined as non-routable address space. Non-routable address space is basically exactly what it sounds like. They are ranges of IPs set aside for use by anyone that cannot be routed to. Not every computer connected to the internet needs to be able to communicate with every other computer connected to the internet. Non-routable address space allows for nodes on such a network to communicate with each other, but no gateway router will attempt to forward traffic to this type of network. This might sound super limiting, and in some ways it is. In a future module, we'll cover a technology known as NAT, or Network Address Translation. It allows for computers on non-routable address space to communicate with other devices on the internet. But for now, let's just discuss non-routable address space in a vacuum. RFC 1918 defined 3 ranges of IP addresses that will never be routed anywhere by core routers. That means that they belong to no one and that anyone can use them. In fact, since they're separated from the way traffic moves across the internet, there's no limiting to how many people might use these addresses for their internal networks. The primary 3 ranges of non-routable address space are 10.0.0.0/8, 172.16.0.0/12, and 192.168.0.0/16. These ranges are free for anyone to use for their internal networks. It should be called out that interior gateway protocols will route these address spaces, So they're appropriate for use within an autonomous system, but exterior gateway protocols will not. We've covered a lot in this module, and congratulations to you for sticking with it. Next up, we'll cover the transport and application layers. But first up, another quiz. You can do it, and remember, you can always go back and review the material as much as you need to.